So the next talk is Celery and Kubernetes for a fast, scalable, and robust workflow orchestration by Param Rajani.
Hey, hello everyone. I hope I'm well audible. Uh, Thank you for choosing to join this track today. Uh, yeah, thank you for joining in on Celery and Kubernetes. And before we jump deep into this topic, I'll start with a quick introduction about myself first. So I recently joined GoDaddy as a software engineer, but prior to GoDaddy, I have about 3 years of experience as a data engineer where I have worked with a couple of product-based companies uh, in fintech and Gen AI domains. And during my time there, I have built product architectures and data pipelines for them on both serverless and Kubernetes platforms, and I've like spent a lot of time optimizing performance and scale on both of them, and this gave me a really good chance to deeply understand scenarios where they scale really well, and also some scenarios where they fail to. And also that's part of the reason why I also have Kubernetes for my talk today. So yeah, let's get into that. uh, so let's set some context. Many of you in your journey may have come across this tool called uh, AWS step functions, or you may have built some data pipelines using Apache Airflow. um, what these tools do is they are supposed to help you orchestrate your workflows. Like you define some steps, like a step A runs first, then a step B runs first, then a step C runs first, and so on. Now, these are like really powerful tools because they allow you to logically break down your complex use cases. But this power that you see here indeed comes with a cost. And these costs are noticeable when your system starts scaling, especially when you have a customer facing system like you see on the screen, where we have a customer's stock buying and selling journey that is made of using step functions and lambdas. This system becomes a problem when a lot of customers start swarming into this, because one is the Lambda concurrency, of course, but you will also have to counter in the cost of each customer, each Lambda function they might go through, and then there's a state transition cost of step function as well. Yet, this sort of pattern is really famous, especially when the companies start out building their products or MVPs, because this scales really well. Like this solves most of the problems in scaling, but eventually, when you reach at a higher scale, this pattern leads to some or the other sorts of failure. And that's why I kind of looked out for an open source alternative, and that's how I ended up discovering Celery. Now, Celery has been very famous in the Python community for years, and I think PyCon 2024 as well had one talk about Celery. Uh, so, Celery, which is popularly known for handling background tasks, turns out can actually do a whole lot more. And this talk that I have here today is like based off on a real life use case where I was a part of a project where we led the transition of an entire product architecture from AWS Lambdas and step functions to a Celery and Kubernetes based setup. And through this talk, what I want to deliver is that Celery is a great open source alternative for this cloud based orchestrator. And I also want to draw some parallels between step functions and Celery along the way. So here's what we are going to explore in this talk. We'll start with a quick introduction to Celery, just a refresher for everyone. And then we'll take a look at how we can build our complex workflows using Celery Canvas. Then we'll move on to explore a bit on compute and scaling with Kubernetes. And then finally end this talk about observability best practices. So let's jump in. So let's understand what Celery is. Uh, Now, Celery is a distributed task queue system. In very simple words, it allows you to execute your Python code asynchronously in a background. It starts with the producer on the left, uh, which could be usually your web app or a backend service. And when this app needs to perform some time-consuming task, let's say it wants to process a file or process an image, it basically sends this request to a broker. Now this broker in between is a message queue. It could be like Redis, RabbitMQ, or an SQSQ, and it holds this request in its own storage until it can be consumed. Now, the consumer or the worker on the other hand is subscribed to this broker, and it pulls these tasks from this broker and does the actual execution. Now, this very simple flow of producer, broker, and consumer is like the very backbone of Celery's task execution model. This is a very simple example of doing this. Uh, on the top, you have an application which wants to generate a Ghibli image. Now we know that it takes an annoyingly long time to generate an image like that. So what the app does is it sends that task to a broker. Now on the other end of the broker, you have a Celery worker, which will consume this task from the queue, and it will do the actual generation of the Ghibli image. And this is also the very definition of a Celery worker. It is the actual machine or the process that does the task execution. It knows what the task is from the queue, and it knows how to run it, whatever the code is. And it is constantly listening to that queue as soon as they arrive. Uh, Now, this is how you start a Celery worker. You basically give this command celery dash a tasks worker, which basically tells that, hey, Celery, this is the tasks.py file. I want you to start a worker process. In the previous slide, we have a tasks.py file defined. And you give this command. Let me show it with a pointer. Then you basically mention dash dash queues, which is you telling worker to listen to this particular queue. Then you also mention some concurrency settings, which basically tells the worker that it can process 4 tasks in parallel. This is kind of a useful option when you have multi-core machines. And this log level basically tells you what sort of logs you want the worker to emit, info, debug, warn, whatever may be your use case. But the thing about Celery is that it is much more than a background task, and this is where it really shines. Celery can enable complete orchestration capabilities where you can define logically how tasks are supposed to be chained or how tasks are supposed to run in parallel, and even retry anywhere in between if something goes wrong or fails. And the best part is about Celery is that it's all written in Python, only in Python. Uh, Now, Celery's Canvas workflows is the tool that gives us the power to build this complex orchestration logic. And like I said, the only difference as compared to AWS step function is that you write all your orchestration logic in Python. You don't create your uh, DAG in a JSON format or deal with a UI based editors. You express it completely in code. This example that you see here on the top is an example of a linear task execution where a task A runs first, then a B runs first, then the task C runs first. And how you write it in Celery is quite simple. You simply import a chain class from Celery, and then you pass in all the tasks and the arguments for them in that chain. And then Celery will handle the sequential executions of these tasks. And while doing the sequential execution, if any of these tasks fail, Celery can also handle the retry and error handling if you define them. So Canvas is not just about chaining the task, it's also about building resilient and dynamic workflows in code. Now, this is another example from Celery where you want to execute tasks in parallel. Let's say you want to download some files from multiple sources. Then, how you would do it on Celery is that you would use a class called group. You would import it from Celery, create a list of tasks that you need. It can be all conditional, whatever you need. You can also skip what you don't need, and just pass in the list of tasks into the group, and Celery will handle the parallel execution going ahead. Now you might be questioning, okay, in the first part I just said that okay, Celery is basically a worker that subscribes to a queue and processes tasks. Now I showed you that Celery can also help you orchestrate workflows using chains and groups. Now, how do these dots connect? How would Celery basically know that the task A, where it generated a Ghibli image, would connect to task B, where it has to notify the user that the image has been generated? And the answer is pretty simple. Celery actually handles this by itself. Now, if you see this diagram, we have a producer. Now, whenever a producer produces a message to the broker, it always hits the exchange first. Now, this exchange that you see here is a part of the Celery's configuration and the queues that you are using. Now, now this exchange basically looks at the name of the task and determines where this particular task needs to be routed, to which queue this task needs to be routed, and there will be an appropriate Celery worker on the other hand that will be listening to this queue. Now, this is an example in code where you basically define that a task named tasks.heavy task always goes to a high CPU queue, but a task named tasks.quick task always goes to a low latency queue. So when you're using chains or groups, and when there is some sequential execution happening from task A to task B, during that transition, uh, this canvas will always first check the exchange and then determine, okay, this next task has to be routed to this queue, and then there will be a particular worker working on it. Okay, so far now we know what Celery is and how we can create our own orchestration. It is now time that we go ahead and deploy it. Now, when we speak of these cloud services like AWS Step Function, scalability is something that is managed completely by them. And compute, on which our code runs, also depends on the underlying service we use. Let's say if we use Lambda function, for example, the compute options are kind of very limited. You can configure your RAM requirements you need, the maximum runtime you need, and yeah, that's pretty much it. Again, scalability is something that you won't need to worry about there. But when we are using Celery, we need to define our own compute and scaling configurations, and we'll take a look at how Kubernetes will help this in the next few slides. Now, this diagram, I know it's kind of looking scary, and I will break it down for everyone. But this diagram comes from an actual production use case which we migrated from step functions and lambdas to a Celery and Kubernetes based system. And the idea is that the complete workflow that you see here runs only using Celery canvas. Uh, and the way it works is we start with a Celery chain, a basic Celery chain of 3 steps. It is a process initiator, a dataset initiator, and a service initiator. Now, each step in this chain can have its own logic of its own internally, and it can also have its own workflows. Now, let's say if you see this dataset initiator, for example, the goal of this task is to simply generate a customer's data set at a very high level. Now, internally, this dataset task would be using a group, and it will basically parallelly fan out to multiple tasks for the datasets that it need to generate. All these can be using pandas and machine learning internally. Now, it can also have some decision making of its own, like what tasks it need to generate, what tasks it can skip. But the core logic that I'm trying to deliver is that uh, a- all of this orchestration can happen using only Celery canvas workflows, and the task execution that you see here is distributed across different worker types. Now, where does Kubernetes comes in? Now, each worker that you see here, where the task execution will happen, runs as a separate Kubernetes pod of its own, which can also be scaled independently based on their own resource requirements. Now, when I say a dataset worker that you see here, like I said, it uses pandas and machine learning. So this is a very high CPU and RAM intensive task if we are to talk about. But the analytics worker might be doing some lightweight aggregations, or it might be doing some API calls. So the CPU and RAM requirements for this worker would be very less. So this architecture gives us a massive flexibility to define what should be the compute options for this pod. Now, the interesting thing about combining with Celery with Kubernetes is the interesting design decisions that it allows us to take. Now, if you see here, uh, we can have each task work on its own dedicated worker, and we can scale that worker independently based on its demand. Now, on the other hand, we can also have multiple Celery tasks work on a single worker, but and this will simplify deployment and operational overhead. But this sort of pattern is only possible when the tasks that are grouped together don't interfere with each other's performance and time. So we lose some granularity here, but we gain something in manageability. Now, what makes this even more powerful is the ability to scale based on queue metrics. And like you can say, the number of pending messages in the queue. You can hook one of these metrics into your Kubernetes autoscaler, and you can simply increase or decrease your number of pods, which basically means more workers subscribing to the queue based on the demands, like how many messages you have in the queue. And if you take a close look at this sort of scaling, you can see that you're close to building your own Lambda functions, but you have your own customized compute. So this is why it makes it really powerful. Now, this is how a typical Celery deployment would look like on Kubernetes. What we are basically trying to do is we are trying to deploy each specialized worker with its own resource profile and execution model. Now, if you see on the left, if you see the commands closely, we are using a uh, okay okay all right. We are using a pre-fork worker pool over here. uh, and pre-fork worker pool is like very good when you are using a CPU intensive task. And if you also see the resource requirements, we are giving like 2 GB of RAM and two full cores of CPU. And it also has a concurrency of 8, where this particular pod worker can execute 8 tasks in parallel. Now, if you see on the right hand side, we have a light worker. And if you see, it uses a G event worker pool. Now, G event worker pool is good for IO intensive task where you want to do some small database fetch or you want to simply call an API. G event worker pool is to go for. But if you see the requests over here, is very less as compared to the left hand side. The CPU is like only a zero point 0.5 core, and the memory is also like half a GB. And the concurrency is the quite an interesting part. You see, it's like the concurrency of this is 100 as compared to the concurrency of 8 on the left hand side. So this is like the combination of Celery and Kubernetes working together. Each worker, of course, run at its own separate pod, which can be scaled independently on demand. But the fine tuning of these settings that you see here, where you have concurrency, resource request, and the worker pool, makes this like very flexible and scalable in terms of compute. So yeah, that's a little bit about compute. Now we'll move a little bit on the observability side. Now, if you may have used tools like step functions or Airflow, you may have noticed that it has a really cool UI. Step functions, if you see, it shows you the tasks which ran successfully, the states which failed, or the states that are running in progress. Airflow, on the other hand, also has a cool UI where you see all your DAGs and operators, and it shows you in a really nice color combination as well. But Celery, so far we've discussed, is only like a Python library that's allowing you to do this, but it doesn't come with its own UI out of the box. So if we are to deploy something with Celery in production, we will need to take care of the observability stack, because we cannot stay blind with our own real-time pipeline running in production. So this needs to be best integrated with our own custom observability stack. Now, the first stack that I found very cool was Sentry. Now, Sentry developed its own SDK for Celery, and it basically configures in like a 4 to 5 lines of code with your Celery configuration. And anywhere in your workflow built on Celery, if you encounter a Python code error, Sentry will do the task of raising an alert, and it will send it over to your Slack or your email address with the entire stack trace of the error. The stack trace, like, of course, will consider which line your code failed or whatever. Now, the second most impressive stack is the EFK stack. Now, I know EFK stack would be a little bit complex to deploy and manage, uh, but this stack is well proven for Celery. And the cool thing about Celery is Celery gives us some features called Celery signals, which allow you to run some code before and after a task executes. And in that line of code, you can basically write your own logger statements, like what parameters are going into that task, or what is the metadata of that task. And when these logs reach your Kibana dashboard, you can see here, you can basically apply your filters and see what's going on. Like, let's say if your logs have a unique identifier, let's say if you have a identifier of a customer ID, you can simply apply a filter on this, and you will see all the logs only particular to that unique identifier. And you can also see which task it was going to run and what is the status of that task. So if you like apply a filter on that, you can see that particular identity had gone through all the tasks, which failed, which went into retry. You can see all the status of it. You can also put a filter on the task name, and then you can determine how that particular task is basically performing in your entire workflow. You can get all the timing information and everything going on. So coming back to this product architecture, which I showed before, when we apply all the tips and tricks, we get a workflow on which we have full control over the compute, the types of node we have, and the CPU and RAM. And we can also have our own custom scaling policies which can handle different sorts of traffic patterns. And with the right decisions, this workflow can be made very customizable. You can add more components to this, remove components, but with Celery you can simply define very customizable journey for your customer. And the best part about this is, before we migrated to Celery and Kubernetes, the previous Lambda and step function approach would do 30 seconds, would take 30 seconds to process each customer end to end. The same customers on Celery and Kubernetes setup took only like 8 seconds. Now, obviously, this is not just Celery and Kubernetes. We might have also done a lot of code optimizations. We have also played with a lot of Celery configurations, which I have not covered into this. But as a solution, this setup can handle fairly high request per second over the other AWS approaches. So this is a quick differentiation between a Celery and Kubernetes setup and a step function Lambda setup. The cost drivers, if you see on Kubernetes, will depend highly on the EC2 compute and the EKS services. But to manage that infrastructure, you would also need a team of good DevOps engineers. So that's also a part of cost drivers. But on step function and Lambda, the cost will basically depend on Lambda's execution mod cost and the step function state transition cost. The concurrency on Kubernetes is virtually unlimited. You can scale as much as you want. But when it comes to using a Lambda based compute, you are kind of limited to 1,000 concurrent executions, which can be increased to an extent. But again, this is not very unlimited and not the desirable approach as well. Scaling behavior with Kubernetes is something which you have to define by yourself. uh, you will have to do many iterations of load testing. You will have to iterate various traffic patterns on this. But once you are able to do that, once you analyze through all those load testing, you can scale this for a fairly high request per second. But step functions and lambdas will provide you effortless scaling, and that's why this is also really good for starting out your products and building your MVPs. Control over compute, like we previously observed in the slide, Celery and Kubernetes really give you very fine-grained control, which as compared to the Lambda specifications, you are kind of very limited to only configuring your RAM. So Celery and Kubernetes is ideal in scenarios where you need full control, you have a very large scale, and you also have a team of engineers that would be dedicated for this. But step function and Lambda is something that is good if you are starting out. you want to achieve scale quickly, you want to get your product out in the market, then step function and lambdas is to go for. So yeah, that's it about this talk. Hope you guys enjoyed it. These are some key takeaways. We finally know Celery is a good alternative, and Kubernetes can give us the control over compute and scaling. And with the right observability systems, we can ensure reliability and error tracking. So yeah, that's it. Thank you guys. Do we still have time, or so do we want to move in for Q&A? If anyone, yeah, sure. Yes, yes. So what you are saying is kind of true. It does not. I mean, Celery and Kubernetes will come with more operational overhead. Uh, but that's the time when you are scaling really, really high, and you will need to invest on that. So you should it will increase your manageability, and you should invest in that. But again, if you don't have that scale, best go with Lambdas. It'll just quickly get you up and running.
Okay, so you talked about the fine tuning for
Yeah.
salary task. So which all parameters to consider for this, like
Okay.
how you come to final conclusion?
Yes. Okay. Let me move to that slide again. This one, right? Yeah. Now, yes, uh, we did have in our workflow steps. Do you see that dataset worker there? Now, the core idea of that dataset worker was to use some pandas and machine learning within it. Okay. So now this is something that we discovered that obviously prefork worker pool would be the best. Celery by default uses the prefork worker pool even if you don't mention it. So uh, Celery has a documentation where they say that if you have a CPU intensive task, use this, and where you have IO intensive task, use G event. Now take a look at this dataset initiator. Okay, like this is also a worker that is doing some task. The task that it is doing is it's basically distributing the various different tasks that dataset generation it has to do. Okay, this initiator, if you see, is not doing any CPU intensive workload. This can be made G event. And let me tell you, we did this mistake. We let it run on pre-fork, and we found that we had to scale the pods for this as well, even if it wasn't doing anything. When we switched to G event, this became really fast. Even a single worker instance of that was doing a lot of work. So yeah, we did some experimentation and documentation referring for that. Yes, yes. Profiling for data sets we did because, like I said, it uses machine learning. So we had to load up the models in memory. So what we did was we did some local profiling. Like we just made a Python script, loaded the models, and just ran the trace malloc. Like it gave us how much memory it consumed during runtime. So I got an estimate that okay, this much RAM should be enough. Yeah, sure.
Hey, so let's say there is a big task which has both CPU intensive and IO intensive
Mhm.
operations inside that. So which approach is better? Is sh- let's ha- should we have a single task, single salary task, or shall we use that chained
Chain.
task thing?
Chain would be better because the IO intensive task, like I said, right, can run on very small resource. You don't need too much RAM and CPU requirements there. So best to decouple it as much as you can. Uh, Unless both solve the same business logic, then it might make sense to keep it together, but decouple it.
But if it is sequential, that IO tasks depend on the previous CPU intensive tasks that were getting
Yes.
executed. So will that be taken care that it should be sequential and
Yes, it will be taken care. It will run only one after the other. First finishes, successfully finished, then only it moves to the next. It won't move to the next without that.
got it? Thank you.
Share data between stages. Oh yeah. But for that we had different things. I mean, we used S3. and Redis. So whatever data sets that we generated on the first step, right, we would basically store it, but on the second step, we would usually read it. Yes, you're saying over here, right? That would this wait for everyone before? Yes. So Celery has an option. So when you are doing a group, right, where you are parallelly executing between multiple tasks, there is a option. I don't remember it, but I'll go into the documentation. We can check it together. But what it does is it waits. It waits for all of them to finish first, and then once this has finished its execution, then it will move to the next step in chain. So yeah, if you are telling me that while executing this is like the runtime blocked, yes it is. Yes it is, and that's where also G event helped us. Pre-fork was basically blocking the runtime and just blocking that particular worker from executing anything else, because it was simply waiting on the other data set task, which itself it wasn't performing, but it was basically blocking the runtime. G event, what it did was it basically waited for it, but it while waiting for it, it would move to the next task and uh, uh, do its own parallel fan out for that.
Yeah, I have one question, which is according to your experience, which message broker you have found like more stable? So I have a like very bad experience with Azure Service Bus. It just like work for like some time and it just get disconnected, the broker connection. I tried couple of Celery's by default environment variable and couple of tweak, but it's just get disconnected. Then I shifted to container apps and I use I think Kada. So now it's working. But if you are directly working in like Linux virtual machine, it just like Celery's connection is just get broken sometimes.
Like does it happen that after a few hours it just stops consuming the task? Does it
Yeah,
happen
yeah,
something
yeah,
like
correct.
it?
Like
It did happen.
it just go into
It
sleep mode.
it did happen. I used SQSQs, and what happened was like after 8 to 10 hours, it's just stopped responding, and I unfortunately didn't have any solution, so I kind of ran like a cron job to restart that
Okay.
worker. But
Actually,
yeah,
then I shifted to Redis and I found like with Redis, it is like very stable connection.
uh,
So yeah.
oh,
And I also
that's
another
good.
questions.
Yeah,
Sorry.
yeah, sure, sure.
Yes. Another question, which is like, let's say I'm running a agentic kind of a like operation, very small operation,
Hmm.
where I have tools, kind of like let's say calculator based tools.
Hmm.
So I agentic application, it's kind of a async. It's calling the third party APIs, but there are also like some of the tool calls. So in that kind of scenarios, which kind of worker do you suggest, like G event or pre-fork?
It's basically APIs only.
Yeah, API
It's
and plus like tool calls as well, because
only APIs. G event would be to go for, yes.
also like even if there are tool calls like computational tool calls like calculator tool which is running in like pure Python.
Pure Python, like within the code
Yeah,
itself.
within the code itself.
I think G event should work, but if as long as you're not doing any very computational heavy, uh, like like I said, pandas was a big thing.
Oh,
Compared to pandas, if you are telling me it's a simple, very small computation, then it's fine. Maybe
okay,
try
cool.
G event for it.
Yeah, cool. Thank you very much.
Oh, it's done. Thank you, everyone.